biogeochemistry, so he's interested in the cycles, the big cycles, and mostly under the AGES project. He's coming here, but he will explain probably much better than me. He's coming here as part of a team looking at the resilience of the coastline, and the job we've done together so far was to try to determine the amount of groundwater diffusing into the lagoons for reasons that he's going to explain. So I'm not going to spend much more time. I'll let John start, and we will have about 30 minutes of presentation, and then you can ask any questions.
First of all, thank you, Jerome. Thank you to all of you for being here today. I really appreciate the opportunity to come and speak with you. I may not sound like I have a German accent because I'm not German. I do work in Germany, but I'm from New York originally, and have been working for the University of Kiel on and off for the last 13, 14 years. And this project, what brought me to the Seychelles, is a project called ADJUST. And what is ADJUST? Well, ADJUST is a project that's actually a philosophy project from a professor named Christian Batz and a few of his students. And this project is trying to essentially understand the fair distribution of funding in small island developing states that's associated with problems attached to climate change. So what's interesting is money is often given without any understanding of where it's going, how it will be used, and how it will be distributed. And the main point of the project ADJUST is to actually track that, to understand it, to talk with different stakeholders, to talk with different countries, to better understand how we can more fairly distribute money amongst these countries, amongst small island developing states. And so I'm here as part of that, and I'll get into why in a second, but just I briefly want to just go one further slide into introducing the project ADJUST. It's essentially 5 work packages. The first work package is to understand what is the status quo of adaptation finance. So basically, we or the European Union, the United States, UN is already sending money to small island developing states to better adapt to climate change. But there's no real criteria behind that distribution of money. So the first work package is to understand what is happening today. And the way they do that is they interview, and this is not really me, it's more Professor Christian Batz, but they're interviewing bilateral donors, interviewing the multilateral climate funds, who are the recipients, any documents that are coming out about this distribution of funding, they're analyzing those documents. So once they have this status quo, they're going to try, and I want to stress try, to understand which procedures and criteria that are already in place are justifiable and practicable. And so this leads to work package 2, which is essentially a critical reflection of this distribution and the procedures and criteria associated with the distribution of funding. Once they have that, this leads to the next 2 work packages. I'm going to skip work package 3 for a second. Work package 4 is democracy, so trying to understand and analyze the justification of where the money is going. Right? So this is all philosophy to this point. It's all philosophy. But there's one other work package, and that's where, let's say, environmental science comes in. So the main issue associated with climate change is vulnerability for small island developing states. So we talk a lot about vulnerability. We talk a lot about adaptation, but we first need to understand what that vulnerability is. And so this work package 3, is trying to focus directly on Seychelles to better understand what is the vulnerability of Seychelles to climate change, and more specifically to sea level rise on Seychelles. And so that's more or less the main reason I'm here. Just quickly, all of these will then come together for the final work package, which is to actually have an outcome of this project, to make recommendations to policymakers, to stakeholders on how best to distribute that funding. This is a 5-year project. It started in 2020. We're right in the middle of it in 2023. It'll finish at the end of 2025. There will be a workshop sometime in the middle of 2024 where they're going to already hopefully have summarized the first 4 work packages and discuss how to get to work package 5. So just summarizing again, there are 4 work packages before the summary work package. And the one that I'm here for is this vulnerability work package. So to understand the coastal impact of sea level rise in Seychelles. This is one of the reasons why I'm here. Now, we've already had a couple people here previously, about a year ago, and they started to do this work. So the main person who's working on this is a PhD student in Germany named Dorothee Fehling, and she's using 2 models to better understand what that vulnerability is. The first model is something called DIVA. Has anyone heard of DIVA? It's the Dynamic Integrated Vulnerability Assessment Model. And basically, DIVA has been used on a global scale for the last 10 years to understand vulnerability on a global scale. And the way it does that is it takes the 2 main sources of sea level rise. One is natural subsidence or uplift. So subsidence happens when you have sediments that compact over time, and so land sinks. A good example of this would be Venice, right? So the city of Venice is in this lagoon. That lagoon is just loosely consolidated sediments, and the city sinks slowly over time. Then there's glacial isostatic adjustment. Has anyone heard that term before? Sorry, I'm also a teacher. So glacial isostatic adjustment is probably not affecting Seychelles. But in a lot of parts in the upper latitudes, a lot of parts of the world in the upper latitudes, the land is still adjusting to the last ice age. So in places like Norway, you had a very thick ice sheet above the land. And there was a lot of weight above that land. And so it literally pushed the land down. Once the ice sheet melted, it's coming up. So Norway doesn't have sea level rise issues. In fact, Norway is going up. Norway is going to have more land than Sweden and places like that. But places on the edge of the last ice age, places on the edge were actually pushed up during the last glaciation because the weight in the middle, it's like lying on an air mattress. You ever lie on an air mattress? Where your body is in the center, it goes down, but the edges go up. Right? So that's what happened on the edges of the last glaciation, and those areas are sinking really fast. So it takes into account subsidence and glacial isostatic adjustment. These have nothing to do with human impacts. These are natural impacts. Well, subsidence can happen. Skip that for now. The other thing that it is looking at is regional climate change scenarios. So sea level rise is happening also at a regional level. So there's a lot of information out there that's looking at different rates of sea level rise around the world. See you guys. And so what DIVA does is it takes into account sort of this natural sea level change scenario as well as the climate scenarios. It puts them together and it gets a total idea of relative sea level change over time. And then with that, it starts to look at what the potential vulnerability is. So vulnerability can be flooding. Right? So how often is your land flooding? How often is it being submerged? What is happening when your land is flooded? Are people leaving, migrating away from it? Or are we trying to protect that area? Are we building flood retention structures? Are we building things like sea walls to prevent coastal flooding from happening? The model also looks at wetlands. One of the reasons why it looks at wetlands is because wetlands tend to attenuate flooding, right? So wetlands are an area of natural friction. So when you have things like mangroves and water or flood wave comes around mangroves, the mangroves really prevent that inundation from penetrating far into land because of the friction. This was a big thing during the Indian Ocean tsunami in 2004. In areas that had very intact mangroves, you had a lot less damage than areas where the mangroves were cut. So it looks at wetlands and it tries to value the wetlands. Finally, you have erosion. And the difference between erosion and flooding: flooding is generally temporary, erosion is more permanent, and so this is land loss. And when you have land loss associated with erosion, what happens then? You have migration. Finally, DIVA also looks at socioeconomic scenarios. So it's not just what's naturally happening out there, but it also takes into account the places where it's happening. So for instance, the Netherlands will have a lot better chance to adapt to sea level rise than, for instance, Bangladesh, right? Because just the resources in place in the Netherlands are so great, and also their expertise over years of taking land back from the sea, that their vulnerability is different than Bangladesh's vulnerability. And finally, the DIVA model will suggest adaptation strategies, for instance, building dikes or re-nourishing the beaches. So we have this for the whole world. What's happening now associated with Project Adjust is that Dorothee Fehling is now taking this model and looking specifically at Seychelles at a much higher resolution than the global model is. So she's segmenting the coastline based on population patterns. So is it rural, is it dense rural, is it urban? She's segmenting the coastline based on whether it's a fluvial plain or a non-plain, what the response might be, and whether it's rivers, deltas, and then she's going to come up and she's going to be able to tell you, hopefully, within the next year or so, which segments of the coastline are most vulnerable to sea level rise. In addition, she's also using a hydrodynamic model called list flood to look at what could be a potential inundation area when you add 80 centimeters of sea level rise, which is what NASA suggests is the 100-year sea level rise here in Seychelles, on top of the highest flood level in the last 40 years, which I believe was in 1997, measured at Point Larue, which was 2.3 meters above normal sea level. So if you take 2.3 meters and add 80 centimeters, essentially you're at a 3.1 meter flood above the current datum, which might not be the current datum that I have to find out about. But at that point, these areas in blue, and I'm sorry you can't see this better, but areas that are in blue are areas that will be inundated. So what you see is most of the reclaimed land around Victoria will be inundated, and you have to, I'm really sorry about my pronunciations, areas like Ascertain, up in Portland, thank you. Those areas will be inundated with 80 centimeters of sea level rise and a maximum flooding event. And she's really trying to nail this down. But the thing is, a model's just a model. It's just a model, right? And in real life, there are differences between a model and what's happening. There are things that need to be put into a model to better understand it. What are the current coastal protection structures that are out there? So, for instance, are there pilings in the water? Are there seawalls? Are there jetties? Are there stones? What does the vegetation look like in the area? Is it mangroves? Is it something else? And also, we need to have some real data. So one of the things that I'm doing while I'm out here is I'm putting pressure sensors into each of these locations to look at how high water level is actually going. I'm doing this with the help of those guys in the back corner over there, as well as the DRMD, to try to identify good spots to put these pressure sensors out. One of the places I put it out is in Praslin wetlands, so on the west side, and so like in a little river that's flowing through the mangroves. So this is an intertidal area, and so we can actually get the tidal height and try to match that with her models and current levels. Now all of these pressure sensors have to be, to get good data, have to be left in place for at least the spring neap cycle, so 14 days to understand kind of your true tidal cycle in the area. And then when we have this, we can use this data to ground truth Doro's model. And what I'm hoping to do is leave these pressure sensors here so we can gather more data over the next 6 to 12 months to really refine that model, especially if there's going to be some sort of inundation event. Right now there hasn't been any major inundation events while I'm here, but maybe there will be. I'm not going to say fingers crossed because that's not really a good thing. Okay, but why am I here today? It's a bit of a mixed story. I'm going to try to now quickly talk about submarine groundwater discharge. And what is submarine groundwater discharge? And why does this have anything to do with Project Adjust? Why do we care about this? So when I was coming here, a little bit of an email got sent around and said that I'll be here to learn about Seychelles. And Jerome emailed me and he said, hey, I heard you do radon work. And would you like to look at submarine groundwater discharge right here, right outside of this university in Australia, to see if we actually have groundwater coming into our coastal zone. So why do we care about groundwater coming into our coastal zone? And what are we talking about when we talk about groundwater coming into our coastal zone? So first of all, I just want to make this point right now. Groundwater coming into the coastal zone could be rain that fell on land, goes into your ground, and comes out, right, somewhere. But it can also be a recirculation of seawater. So during high tide, the water goes up onto the sediment, it goes into the sediment, and then comes back out. That can also be considered groundwater because they all have chemical processes that are important for coastal ecology. So we can have recirculation of seawater, and we can have direct fresh groundwater flowing out. Generally, though, we are much more concerned about fresh groundwater flowing out than we are about recirculation. So we're going to talk a little bit about that today. First of all, the question is, how does this fit? How does this study of groundwater fit into Project Adjust, or is it just our interest that we're doing this? And I'm going to have to go back to my bosses in Germany and say, yeah, well, so it's some groundwater work. Now, there is a reason why, and I'm going to try to explain that as clearly as possible. So groundwater, when you have rainfall, and the rain falls on agricultural land, or let's say any land with high levels of nutrients, that groundwater may penetrate, or sorry, that rainwater may percolate through the ground and bring all those nutrients into the groundwater. Those nutrients then flow with the groundwater. So the nutrients I'm talking about, nitrate and phosphate, which is water chemistry, we get into water quality. It's coming then out into the coastal zone, right? Why does that matter? Because when you have a lot of nutrients coming out into your coastal zone, you could potentially have things like algal blooms. We know a lot more about rivers than we do about groundwater. We can measure river flow a lot easier than we can measure groundwater flow. But groundwater may be the main source for nutrients to get into the coastal zone. So why do we specifically care about that here? Well, we care about that because this groundwater and the flow of nutrients could potentially provide a unique ecological niche for seagrass. So it could be a place where you actually have a wealth of seagrass, but it could also be a significant threat to coral reefs. So why does that matter? Well, both seagrasses and coral reefs help prevent or help reduce vulnerability to inundation, help reduce vulnerability to sea level rise. So we've done this work. We did this work in Jamaica to start. So why am I bringing up Jamaica? Jamaica is also a small island developing state. Jamaica has a disproportionately large amount of fresh groundwater coming into the coastal zone compared to seawater. And Jamaica has a problem with coral bleaching. So a lot of the coral reefs around Jamaica are dying. So there's a big push to restore coral reefs. There's a big push to restore coral reefs. There's coral nurseries all around Jamaica, and many of them are thriving, and many of them are not thriving. And what we found out is that these coral nurseries that are not thriving are all in areas where groundwater is coming out. So we flew around Jamaica with a helicopter, and we took thermal images around Jamaica. So groundwater is usually at a different temperature than surface water, and we could actually spot plumes of groundwater coming out. And then we went there, and I'll talk about the equipment we used in a second, but we went there and ground truth that, and we found really that every location where you had coral nurseries that were dying, or not surviving, you had groundwater coming out. So we care, right? And we're not the only people who looked at it, so there's a picture of me in Jamaica in our little setup, so you can do it on that. And I'm not the only person, we're not the only people who looked at this. Several other groups of people have looked at this and have found it also in other locations around the world. This group in the Philippines found that areas where you have a lot of groundwater flowing out often bring too many nutrients as well as labile dissolved organic matter, and they're presenting a major threat to coral reef ecosystems. This is an important topic for coral reefs. It's probably also an important topic for wetlands, and I can guarantee you something. There is submarine groundwater discharge in Seychelles. I guarantee it. I guarantee it. And why do I guarantee it? Well, simply, there could just be simple submarine groundwater discharge. When you look just straight out here, there are rivers that just hit sand. They don't actually make it all the way to the water. They don't, you see that. But it's not like that water that's coming down the mountain just sits there. It's going through the sand into the coast. That's submarine groundwater discharge. Maybe a little less interesting than the deeper submarine groundwater discharge, but it's definitely happening. You have submarine groundwater discharge in Seychelles. The other reason why I believe you have submarine groundwater discharge is you have a lot of elevation, you have a lot of rainfall, and you don't have that many channels coming out and that big of a channel. So that there's a disproportionate amount of rainfall precipitation, to discharge from rivers. So that water has to be getting into the ground and coming out. Whether it's coming out in springs or in just a diffuse flow, I don't know. How much it is, we don't know yet. Where it's happening, we're not sure. Those are questions that we'd like to answer. That's kind of what we're trying to give you. So, have you guys ever been snorkeling and seen shimmering in the water? Where it's not super clear. And the water, all of a sudden, you're swimming, oh, that's beautiful fish, now I can't see, it's shimmering. That's probably because there's fresh water in the water. The fresh water has a different density, so it doesn't mix right, it shimmers, and you can't see. That means that there's probably a source of groundwater nearby. Probably a source of groundwater nearby. And when there's a source of groundwater, it's likely that it's a major source of nutrients, which could be a problem, or it could be beneficial, depending on what you're looking at. The other reason why I believe that there's a lot of groundwater flowing out is just looking at these granite rocks that you have everywhere. There's a lot of cracks in them. Those are probably made by water flowing through. Right? So there's probably pathways for that groundwater to flow through the granite rocks and into the coastal zone. So there is probably this surface discharge that's happening everywhere. But it's possible that there's springs located around your coast. You got a lot of islands, a lot of coastline, and a lot of potential springs. So that would be something that would be really interesting to look at. Okay. So how do we measure this? How do we measure submarine groundwater discharge? There's essentially two ways. One is via direct measurements, which could be something like a seepage meter, which is essentially a cut-off top of a 55-gallon steel drum. Really good for the environment. You can do it a little bit less. So throw that into the sand, make sure it's partially buried in the sand. Any groundwater that's coming up will displace the water that's in the drum into a bag, and then you can measure it and see volume over time. You can see how much groundwater is coming up. Very simple, and honestly, simple is good. And often in science, we believe that we gotta go high tech. Sometimes low tech is your best answer. And low tech is also more readily available, generally. So we can do this using seepage meters, or we can do this usually using ground conductivity measurements. Also, a relatively simple thing, you just get a pole, you put a couple of anodes on the pole, run an electrical current from one anode to the other anode, and based on how quickly that current moves, you know how much salt is in the water in the sediments. The more salt you have, does electricity go faster through salt water or fresh water? Through salt water. Salt has ions in it. Ions conduct electricity. And so when you have high conductivity in your ground, chances are you don't have groundwater discharge because it's just salt in your ground. But if you have low conductivity, then it's possible that groundwater is flowing through it, fresh groundwater. So those are direct measurements you can make. But there's a problem with direct measurements. Direct measurements are a point in time. Those 55-gallon steel drums aren't very big. Those pole measurements are just a point in time. And even in Australia here, you have, 5 square kilometers of potential surface area that you have to measure. So you need to really do a lot of these measurements. So what we do instead, or not instead, but in addition, is we do indirect measurements using chemical tracers. And the two chemical tracers that we tend to use in groundwater are radon and radium. The reason we use these tracers is because radon and radium are elevated in groundwater compared to surface water. The reason they're elevated in groundwater compared to surface water is because the source of radon and radium is uranium. And where do you find uranium? In rocks. And where do you find a lot of uranium? What type of rocks? Granite. Right? So here you have a lot of uranium in rocks, and therefore you look at, you can't really look at uranium because the decay of uranium is billions of years, but you can look at daughters of uranium, so isotopic daughters of uranium, so radium and radon are two of the main daughters of uranium and thorium. And what you then can do is, because it's elevated in groundwater, you can then go theoretically around your lagoon in a boat, collect samples, and measure for radium or radon. And that's a quicker way to do a large area than it is to put an individual seepage meter in the ground. So when you go out to sample radium, you take large volumes of water, you go to a spot, you collect 50 liters of water, and you filter them through these cartridges, which are filled with manganese oxide fibers. The radium that's in the water gets stripped onto the fibers, absorbed onto the fibers, and what comes through is radium-free water. And these fibers then can be taken back to a lab, rinsed, dried, and measured in gamma spectrometers for 226 and 228 radium, or in a delayed coincidence counter by alpha spectrometry for 223 and 224 radium. It's actually quite nice setup, but you need to be able to collect large samples of water, and you need to be able to take this and get back to a lab. The other problem is I cannot collect, for instance, I couldn't come here with these manganese oxide fibers and collect samples and then try to fly back to Germany and measure them, because these are all decaying over time. There's radioactive decay. And the radioactive decay of 224 radium is 3 days. So that means that within 3 days, I'm only getting half of what I originally had. And so I would theoretically have to get in a boat, get in a plane, get back to Germany, put them on, and measure them. So it doesn't really work.
You can buy that.
Or we can buy that. Yeah. Or we can buy that. These things, I forget how much they cost me, like 50,000. That's probably like 20,000. Not cheap. But we can potentially do it anyway. And we can look at it. We can see if we can time it right. Because when you have radium, you can create a mass balance to understand how much groundwater is coming out. So basically a mass balance says you have a box, and what goes into the box must equal what goes out of the box, or vice versa. So what goes out of the box must equal what's coming into the box. And our box could be Royal Harbor. And so what you have to do is measure what's going out, calculate what's being lost via decay. So you take samples basically at the inlet to measure what's going out on an ebb tide, so the tide is going out. You get samples out in the open sea, which would be exciting with our little boat, to measure what's coming in. And then you can measure what's coming in via the streams. You can measure what's coming in from sediment resuspension. This is a little bit more difficult. And from mangroves and from diffusion, if you can identify all of these things, what's left is your groundwater. And we've done this. We've done this in a lot of places. We've done this in Jamaica Bay, New York, which was exciting because we were putting these big barrels of water up on the salt marsh. The gravity filtered them through the thing. The problem is this salt marsh was directly underneath the plane line to JFK Airport. And when you're in a plane flying over, that looks a little bit scary when you see people on March building that. So they called the police. The police came out, sent the gunships, and luckily they didn't shoot first and ask questions later, which the New York City police is known to do. So we survived, and we got good measurements. But what was interesting is our measurements suggested that we had about 40 to 50 cubic meters per second of SGD going into our bay. The problem is the maximum possible discharge based on watershed area was only 11 cubic meters per second, so it's too high. We then did this in Venice. Just a good picture of me measuring this my little boat in Venice, picking up samples all over this lagoon. We did this 6 times in 6 different seasons to try and see how much groundwater was flowing into the Venice lagoon. And when we got to the end of the study, we calculated 160 to 970 cubic meters per second of groundwater going into the lagoon, which is more than 10 times the mean annual river discharge. It's too high. A few years later, kind of the guru of radium measurements, Billy Moore and colleagues, came out with a global estimate of groundwater discharge. And this was based on 228 radium samples taken all over the world. And what they found was that in the Atlantic and Indo-Pacific Oceans, there's, forget how big that number is, a lot of groundwater discharge. In fact, 3 to 4 times greater than the freshwater flux into the ocean of all the rivers combined. Too high. The problem with radium, and then I'll get to radon and we'll be done, I promise. The problem with radium is that it includes that saltwater recirculation into the calculations. And remember in the beginning I said groundwater discharge is both fresh discharge and salt discharge? Radium, because radium is absorbed on the sediments, and when it hits salt water, it releases. Radium includes both. Radium includes both. Now this can be important. As I said, the recirculation of seawater can be important, but in the case of what we're talking about, especially with coral reefs and seagrass, we're less concerned about recirculating seawater. We want to know about freshwater. So how do we want to do this? What is the solution? So I combination of computer work, namely GIS, radon measurements, and direct measurements. We'll talk about that very briefly. Sorry, I had to talk too long. This is my problem when I teach. So basically, how does groundwater flow? Same way as surface water. Groundwater basically flows, simply put, downhill. Right? It flows perpendicular to equipotential lines, and equipotential lines are mainly based on surface elevation differences. So just like river water flowing downhill, groundwater flows downhill. So we believe that you can use GIS, simply GIS, to locate areas of submarine groundwater discharge. And this is something that anybody can do, right? You don't need a 10,000 euro radon detector to do this. You can locate it just using GIS. And how does that work? Well, basically, you take a digital elevation model. You understand, maybe if you have some hydrogeological information, you can get the equipotential lines. Simply stated, you take a digital elevation model and you use the flow accumulation function. Depending on if you're using QGIS, it's called channel delineation and watersheds. And if you're using ArcGIS, it's flow accumulation. And flow accumulation, it simply uses pixels. So a digital elevation model, it uses pixels. And it tells you, based on the elevation change, let's look at this 44 for a second, which way the water is going to flow. It's going to flow from 44 to 22, right? Because it always wants to flow the steepest downhill. So water flows from this pixel to this pixel, water flows from this pixel to this pixel to this pixel, et cetera, et cetera, et cetera, and eventually you get flow accumulation. You get flow accumulation. And that's how you create channels using GIS. So if you create channels using GIS, and then you look at a map of just a satellite image and you say, hey, I should have a channel here, but there's no channel, that's probably groundwater. So once you have that map, and if you're lucky enough, you have a radon detector, you can then use your radon detector, which is also a daughter of uranium, to go out and look for your groundwater. And why radon and not radium? One quick thing. Radon is a gas. Radon's a gas. It has nothing to do with the salinity of the water. The radon will then, anytime the groundwater passes through the rocks, the radon will just dissolve into the groundwater. And so where it comes out, you have this radon signal. You have this radon signal. And you can then literally go on a boat around your lagoon and look for these radon signals. So we get our radon detectors, which are known as RAD7s. We put them on a boat and we pump. We just chug through our water very, very, very slowly. You can tell them how slowly we went. Very slowly. Very slowly. And you pump water through a water exchanger, water gas exchanger. And that gas then goes into the radon detector and you look for peaks of your radons. There you go. So, we did this in Connecticut. We did this combination of GIS and radon in Connecticut, in an abatement in Connecticut. And what we saw, and this is kind of hard to see here, is that we have flow accumulation wherever these white lines are. Where the lines are quite big, we tended to see them as surface water discharge. It's really hard to see on this image, but there's a lot of white right around here, where it's very small. There's no surface water discharge there. And at that same point, you have very high radon levels. Zooming in a bit, you might be able to see it a little bit better, but there's a lot of flow accumulation right along this edge and along this edge, and you have high radon levels. In areas where you have very little accumulation, you have low radon levels. When we did this in Connecticut, we did the rainfall-based discharge, what can be happening in the lagoon there, we got 1.2 cubic meters per second. When we use radon instead of radium, and we use the basic studies, so not taking into account wind, I don't want to get into there today, it was 0.7 cubic meters per second, so much better than the radium. When we did add wind to it, because wind allows more radon to be lost, our level goes a bit higher, 5.5 cubic meters per second, but still on the same order of magnitude, which what should be happening. And the truth is, this assumes complete loss, this assumes no loss, and the answer is probably somewhere in the middle. So it's a good way to do it. So we brought this here in Australia. And we did a survey here in Australia on the 4th of October, and we looked at radon along the coast of Australia, and you can see down here we have a peak of radon. There is SGD in Seychelles, and because this man's a smart man, he knew it. Before we went out there, he said, this is where we're going to find the radon. I think Stuart lives somewhere around there too. He has a well. There is groundwater there. And so we know this is where we're going to find the radon, and we did. We found the radon. And last night, I did the flow accumulation based on a freely available satellite. I think it was the Landsat image of digital elevation. And what I found was that there's flow accumulation here. Everybody knows there's a little river that comes out, I think, right around there. And that's this river here. There's another small stream that comes out a little further south. And then there's randomly a lot of flow accumulation right here. There's no real streams that are happening right there. Maybe something small I don't know about, but I didn't see it. So it's also a weird flow accumulation. It's not like a river that's coming out here. So there's something happening here. So we can easily do the digital elevation model for all of Seychelles. Easily. Especially if I can get my hands on a high resolution digital elevation model. We can do it for all Seychelles, and then we can see where we should be looking for radon. We can see where we can try to figure this out. So we got this, we started getting this data, and we were really excited, and then our radon detector broke. So all the way here, it broke. Contact discharge. It's like, oh, you don't want to see this. It's like the sign of death. So we contacted Courage, and they said, you have no hope. But they are being nice enough to send us another radon detector, which we'll hopefully get here in the next days. So we have some more time to do it. If not, then you guys can do it without me. But we will hopefully be getting a new radon detector in, and so we can continue the work. So what's next? Next, we want to complete the radon survey of Australia, and then I would like to measure radon in the mangroves, and any surficial groundwater that I can find, or for instance, Stuart's well. This was Jerome's idea. We should measure radon in the pore waters below seagrass beds, and we can do this. That's what this picture is. I should put this thing in the ground and open it up. It's got like a little filter. You suck the water through there, put it into the radon detector. And then you can measure radon in pore waters. I'd like to place seepage meters in the sediment. That's something that we can then do as well, if you have comfort about. And then we can quantify the total SGD into Australia. And finally, if we're happy with our data and we have some funding, we can expand to further abatements around Mahé and maybe other areas. So just to bring this all back in a full circle, in the Seychelles, I think we believe that SGD is likely an important source of nutrients and potentially organic matter into these coastal bays around here. A combination of using simple GIS plus some direct, which I call low cost, and indirect, which are called high cost, measurements may be the best way to understand the SGD around Seychelles in total. If we understand this, potentially we can help locate sites of seagrass and coral reef restoration. So SGD good, SGD bad, right, for the sites. And why does this matter for Project Adjust? Why can I go home and tell them it was good that I did this? Because if we have healthy seagrass beds, if we have healthy coral reefs, this increases the protection of the coastlines and decreases the vulnerability of Seychelles to sea level rise. Okay, sorry guys, that took a little longer than I expected, but I hope it was entertaining. Thank you.
I hope you convince our audience. Do you have any questions? 10 minutes. Yes, all right. Maybe introduce yourself.
Sorry, my name is Mahé. I'm senior lecturer for the environment. Thanks for the talk, that was interesting. I was just wondering, is this SGD variable over time and space? For example, does it just pop up in some places for a while and disappear? Or is it like a consistent SGD pattern over time?
So that's a tough question because it really is dependent on the type of location you're looking at. So if you're in an area with a very direct connection between precipitation and groundwater flow, so in other words, unconsolidated sediments where groundwater flows very quickly through it, then when you have a precipitation event, you tend to have more SGD. If you're in an area with more confined movement of groundwater, usually that's more of a seasonal, more long-term pattern of flow. Often in these areas where we find springs. So we did a lot of work in Mauritius. They have volcanic island, it's a volcanic island, and these lava tubes that come out. You tend to have this just consistent seasonal flow of SGD. One of the problems is SGD can be super temporally variable if it's just a direct unconsolidated sediment because it can be dependent on tide. If you have low tide, you have a stronger gradient between the water level or the water table and the sea level, and so you would have a faster flow. If you have high tide, it's the opposite. We really see tidal variabilities, and this is one thing that we wanted to look at with the radon detector broke, is to look at how SGD is in the Australia at high tide and at low tide. So it's a tough question because it's very dependent on where you are, but yes, generally there's variability.
Tidal pumping due to hydrostatic pressure.
And like over time, has like SGD decreased because of human development, like flow and
So another good question. So when you have essentially human construction, you have more impervious surface. What you have is more runoff directly into channels instead of infiltration into the groundwater. So the groundwater table will drop, the runoff will be faster, you get a lot more flooding events, you get a lot more pulse events, and you probably have less SGD, which could be a problem if you need the SGD for seagrass. It could be good for the coral reefs, look at it. But yeah, human development generally decreases groundwater infiltration. Now, in some cases, it can increase it, right? So if you are building, I don't know, a bridge or a building and you hammer piling through a confining layer, you might allow more groundwater to flow out or more groundwater to come in. So generally, it decreases groundwater infiltration. Some cases it increases.
Another thing that we should think about is, for example, the downsource dam that has been constructed, which creates a retention of fresh water pretty high in the valleys. Then the water would accumulate and flow better to the ground instead of just percolating on the surface and going to the lagoon. So this may increase also the amount of groundwater flowing from this watershed. And on the opposite spectrum, we have the alteration of the wetland in Anse-la-Mouche that has been big hotel removed all these wetland and replaced it by channelized streams, which is very detrimental to the groundwater. we've got on both sides of this mountain two different aspects. One that is supposed to increase, and the other one which is supposed to decrease the number of population.
From your presentation, very interesting. I mean, apologize for groundwater discharge. But maybe I missed a point. I don't see the ratio. You say your project objective was to evaluate the vulnerability of Seychelles. I don't see the link between vulnerability of Seychelles and groundwater discharge.
I think that the only, or the clearest link is one of the problems, or one of the things that's happening here in Seychelles is the coral reef restoration programs. It's happening in multiple areas. I don't know the details of exactly where it's happening, but based on our research in Jamaica, what we find is that those coral reef restoration projects are successful in areas that don't have groundwater. Well, so if you reduce your coral reefs, you increase your vulnerability. Or if you increase your coral reefs, you decrease your vulnerability. Because the coral reefs themselves break the waves that would increase the potential flooding associated with sea level rise and land water.
So coral reef has been proposed by the World Bank as the topmost ecosystem-based solution to fight against sea level rise. And that's what has been promoted in Seychelles for the last 10 years. And there's a lot of money that is channeled through NGOs to conduct coral restoration. And we don't know if it's really efficient or not, because the stretch of the coastline that has been restored for coral so far is pretty small compared to the entire coastline. So maybe there are other solutions that we could explore, like restoring seagrass beds, like restoring mangroves, planting new mangroves in regions where we may have enough groundwater flow to feed these mangrove sediment with nutrients which they need to grow. So there is behind that potential suggestion that can be made for building more restoration sites of more diverse natural-based solutions. No more questions? If some questions pop up to your mind, I can share with you John's email address, and we'll be very happy to answer, because he's also a lecturer, so he knows that questions do not come spontaneously sometimes, and they can come later. I think we can close this seminar now. Do you have anything to say?
Yeah, I do have one comment for all the students in the room. This is a lot of fun, this work. and it requires people to do this research. Right? It requires people that are willing to go out there in the field, collect the samples, people that are willing to, spend an entire day putting these things in the ground and measuring the groundwater that's flowing out. And I'm pretty sure there will be the opportunity for projects like this in the future, but we all need your support to make these projects work. So it's fun. I really recommend it.
I think they are.